Good evening, everyone. Okay, so I don't know, last time somebody was asking whether I can meet you here. I checked with NPTL. It's possible if you're in Mumbai, we can fix a time and we could meet one of the evenings. Maybe email me and then we'll fix a time. Okay? Is that all right? And I remember one more person sent his review paper. I'm sorry, I'm still battling my time with the semester. But I will definitely take a look at it. Hopefully by summer I should be able to do it. And I'll send my feedback. I don't remember the names, but these two I wanted to say. I think those two students, if they are there, they will know what I'm saying. Okay. And how many weeks are over now?
10 weeks.
10 weeks over. Okay, almost you're all finishing, right? Another 2 more weeks, and then you are back to the exam mode. How is it going? People who are online can type and tell me if there is anything which is not clear or you want anything to be clarified. Good evening, everybody. Have anything specific to ask? I can try to explain. Whatever you want to know pertinent to the course will be better. And do well in your exams. I'm sure all of you have registered for the exams. How many? If you have not registered, please register. Exam is the one mode by which, that forces you to kind of revise and get the concepts clear, and that helps you to write the exams. Okay. So just don't do only doing your course by listening and only assignments. Try to take the exams, all of you. Okay. Yeah, you can start typing your questions. We don't see any other question in the portal. You can start typing if you have anything to tell us. You want anything more to know. Okay. So all the harmonic oscillator ladder operations are done. Rotation. Okay. So what exactly you want to know? Is it not? So what is rotation? You all do it, right? You take any object or you take a vector and rotate it by an angle theta. You can do this. Whenever you have to rotate, what is important? You have to say about the axis, which axis you're going to rotate. Like the conventional rotation which you do on the XY plane. Yeah, book reference for quantum mechanics, I have not mentioned. Griffiths is one, which is basic undergraduate level book. If you are looking for a little more advanced, there is Sakurai, which also you can refer. That's modern quantum mechanics by Sakurai. And there are also many other Zetterli has a lot of problems. Worked out problems and exercises. On top of doing these assignments and exercises, if you want to see more problems, that's a very fat book, but I'm sure every library would have it. But Griffiths it's available. I think at a subsidized rate is my feeling. It's an Indian edition is there, right? And for all this
Even PDFs.
content, you can keep that as a guiding book and follow the lectures with that. Okay. So someone asked about rotation group and basic quantum mechanics only I'm saying. Griffiths and Sakurai modern quantum mechanics, not advanced quantum mechanics. Sakurai also has a book on advanced quantum mechanics, but maybe you can type it for them on chat. Sakurai and for modern quantum mechanics, and also Griffiths Also, I forget the title. It says quantum mechanics. Okay. Is Bizer nice? Okay. Bizer is a little, zeroth level as far as I consider. Like, I always say prerequisite to Schrodinger equation, right? All those step potential, reflection, coefficients, transmission coefficient, all these things, I assume you should know it, basic wave mechanics. So for such a case, I think Bizer is okay. But if you want to look at all these bracket notation, getting on to the ladder operator way of looking at harmonic oscillator, Bizer doesn't talk very much about this. Okay. Okay, so let's try and tell the students rotation group now. There is no more questions on the references, but these references were not there in the
First slide.
first slide.
Yes, it was there.
Okay, so you have to help me how to make a board out of this. I can start writing. Okay, so I'm just trying to say that you want to rotate a vector. Okay. To rotate this vector by an angle, you first provide the axis of rotation. Okay. So let's take the z-axis to be the rotation axis. And then you rotate by an angle theta, right, about z-axis. Then how do we write? If this is an arbitrary vector, let me call it as r vector. R vector is x times I hat plus y times j hat plus z times k hat. Right? And you can show that you can write this also in a different notation as x, y, and z. And that under rotation changes to x prime, y prime, and z prime. And that is given by cos theta, sin theta, minus sin theta, cos theta, acting on x, y, z. So that's the rotation, right? Rotation of a simple position vector where I do a rotation about z-axis. So what is the meaning of doing rotation about z-axis? This coordinate remains the same. Z prime is equal to z, but x prime and y prime are a linear combination of cos theta times x plus y times sin theta, right? Is that clear? So then you start working out how to study the groups. So this is what we call it as a rotation matrix, let's say. But I should also specify the direction. So the direction was z. You can start multiplying rotation about the same axis by theta 1 and theta 2, right? What do you expect? It will give you another r with an angle theta 1 plus theta 2 about z axis. Okay. So that's the properties of a rotation group. The rotation operators, if you multiply two rotation operators, you get a new rotation operator. And you can also find for a rotation by an angle theta, you can do a rotation by an angle minus theta, which is anti-clockwise rotation. And that will be the inverse of it because clockwise followed by anti-clockwise will give you identity, right? So you can show that r of minus theta 1 z, r of theta 1 z, that has to be 1. Clear? So these are the properties, and I've just fixed to one axis, which means it's rotation only in a plane, but you can fix to arbitrary axis and you can change the axis. There are some subtleties when you change the axis. If it is same axis, then the order really doesn't matter. You could have done rotation by theta 2 and then a rotation by theta 1, or rotation by theta 1 followed by rotation by theta 2. But if it is not z axis, then you will have complicated. It won't be the order will matter. And if the order matters, then you call it to be a non-abelian. Rotation groups are non-abelian groups because R of theta n hat or n1 hat, theta 1, R of theta 2, n2 hat. This is not same as okay. So this is the property that the rotations, the sequence of rotation matters. If it is arbitrary axis, if it is the same axis, if n1 is equal to n2, then it will be equal. Okay. Any other question on the what exactly was the question? He says, can you explain again rotation group? So this forms a group. This collection of R matrices about arbitrary axis forms a group. For every element, you have an inverse element. You also have an identity element, which means no rotation. So the whole set of all these R matrices forms a group, which we call it as a rotation group in 3 dimensions. And we denote it by orthogonal. They are orthogonal matrices, 3 cross 3 matrices. And S to determine that it is determinant is 1 plus 1. So SO3 group is obtained by using a collection of such R matrices. A collection. Okay. Is that clear? Yeah.
A discussion on angular momentum.
Yeah. So next sheet I need to do. So,
Right. No, left to that. Yes.
okay. So now we did rotation of theta about arbitrary axis, but we would like to do a rotation by a very small angle. Okay. So if this angle is 0, I should get identity matrix, right? Plus a delta theta times some correction. That correction is what we call it as angular momentum. Suppose this is along, let's say, z axis, then this angular momentum is z axis. And typically, to remember that it's a rotation about z axis, I can put a delta theta z. So you have something like this. Okay. So what does this tell us? There is a generator which takes me away from the identity operation for an infinitesimal rotation, or a very small angle rotation. These are called the generators in general. Oops. These are called generators in general. And we are particularly looking for what generator will give you rotations. Clear? What is the generator which will give you rotations? And the generator which gives you rotation is your orbital angular momentum. Once you have this, you can either study the properties of rotation by a small angle, rotation by a small angle by about z-axis, rotation by a small angle about x-axis, and you can do the reverse operation. I told you that if you do it about x followed by z, it's not same as z followed by x. But for infinitesimal cases, if you keep only up to delta theta, it will be same. So you keep it up till delta theta squared. Okay. So you will see that there will be an identity with plus delta theta z, Lz. Okay. And then you will have 1 plus delta theta x, Lx. Oops. Delta theta Lx. Okay. Full screen. Okay. And we want to subtract out the other option, that 1 plus delta theta x Lx Okay, if you do that, then what will you get? You will get terms which are linear, all cancelling, identity will all cancel. You'll be left with delta theta z, delta theta x. What is this changing?
Marks.
This one?
Marks. The marks.
Mouse. Okay,
Double click.
this one? No? Full screen. Will you tell us how to do it then we'll know why it's changing at every tone?
You want the previous page?
Previous page, yeah.
पुराना वाला page change.
Just try
Left extreme.
Yes.
Okay. So you take the thing and then you have Lz Lx minus Lx Lz. Okay. So this is what you will have. What you can show is that this difference can be written as 1 minus. So it will actually give us some proportional to Ly. Okay. This is something which we can show that the rotation, two rotations about z axis followed by x axis and the reverse, you can try to show that it is. So essentially from here, you can show that the algebra of angular momentum will be IH cross LZ. Okay. So sorry, LX, LY. So this is something which you can achieve by studying the properties of the generator for rotation, which is deviated away from identity for infinite segment cases. And that gives you the commutator brackets of the generators. There are, because you can do rotation about x-axis, y-axis and z-axis, there are three generators, Lx, Ly and Z. And the commutator brackets of the three generators is what we call it as a rotation group generators or angular momentum algebra. Yeah.
What was the intention behind Heisenberg's uncertainty?
That's, see, one is experiments have shown that, if you do a double slit experiment, or even with an electron beam, those days they thought it's particles, right? And when they send the electron beam through a double slit, as long as they don't try to put the detector in one of those slits to see whether it will be counting when the electrons are going, if you don't do that, they do see the wave pattern, but they don't know which slit it went through, the interference pattern. But if they put a detector there, they know exactly how many of those electrons went through that slit. Right? Then you know precisely the particle nature of electron. In the process, if you see it on the screen, there won't be any interference. So interference or waves will have a wavelength, right? And de Broglie hypothesis tells you that momentum is related to the de Broglie wavelength. So if you can precisely say the wave nature, you can precisely say the wavelength or equivalently the momentum. But you cannot say anything about its location or the position. So that tells you that there will always be impreciseness in the measurement in general, which is going to be given by delta x delta p. And that should satisfy the Heisenberg's uncertainty principle. That's one way of saying. You can also explicitly do superposition of all possible de Broglie waves. Try to find what is the standard deviation and then show that the standard deviation of the position operator and the standard deviation of the momentum operator satisfies that condition. So Heisenberg's principle only kind of gives us the fact that you can't simultaneously measure position and moment. You can't simultaneously detect location of the particle as well as see the wave pattern. Is that clear? Yeah.
So here, delta theta LZ act like commutative,
Which one?
the one that you just explained.
This one?
Delta theta LZ.
No, there is nothing about
Commutation.
these are parameters. It is these which are the operators. So you can see that if you want to find what is a delta of LZ, delta of LX, then you can try to relate it in terms of the commutator, right? And that will be non-zero, which means you can't simultaneously measure the z component angular momentum as well as the x component angular momentum because the commutator is non-zero. Yeah.
What is Bell's inequality?
Okay, so let me not digress today, but if you are interested, let me just check. There was a nice Nobel Prize talk by Sai, my colleague in the department. I'll try and see if I can find the website. I will share it with you so that you can see what exactly is Bell's inequality. Okay, so there are these maximal states, and basically what it says is that if you take a linear superposition of up and down, and one it's a composite of two objects. Okay, so if you pull one far away and the other one far away, if you measure, if one of the observer measures the state of that, if he says it's up, he can say that the other state, the Bell state, has to be down. Okay? But then the question is that they are so far away that it violates a lot of properties. But then the argument is that you cannot literally check because they are so far away. You can infer that it has to be down, but you cannot verify it. Okay? So there's a lot of interesting things going on in this using these Bell's inequality and what are the entanglement states and so on. If anybody is interested, I will try and see whether I can get the video lecture which I can share. Okay? Yeah.
One guy asks about quantum mechanics research published by a Nobel Prize winner in 2022, but doesn't mention the paper's name.
Tell about quantum mechanics research published by Nobel Prize winner physicist in 2022. So this is what you're asking, the quantum information part, right? Like before you go into quantum information and all these things, you should have this sound knowledge of working knowledge on basic quantum mechanics. So if you understand this, then it can give you a little more insight to go into this quantum information course. Okay? Yeah. So delta, theta, z, Lz act like commuting. Why commuting? Del theta z is nothing but that is just a parameter. It is not even an operator. Lz is a diagonal operator, but Lz will not commute with Lx. You will see Lz Lx is not equal to Lx Lz. Okay. Any other question?
One person asks, can I ask something about something else than this course?
You can ask. If I know, I will answer. But yeah, the live session is mainly for the content which is being taught in this course. But of course, you can ask. Since nobody has asked any question, you can ask. If I have something which I know, I will tell you. Yeah. You can type. In MSc, what does research project basically do? Okay. So using these concepts, sometimes, some students look at situations where it's not that the position and momentum, linear momentum are, you know, commuting. It's not commuting, right? Classical mechanics, you can simultaneously measure position and momentum. Quantum mechanically, you know that you cannot measure simultaneously position and momentum, but you can go further to shorter distance scale. And if you put a point in the XY plane, there could be a situation where, if you try to precisely measure the position component X, the position component along Y can become a little, fuzzy in short distances. This gives us some kind of a non-commutative physics, okay? Non-commutative geometry, non-commutative physics, and how quantum mechanics, non-commutative quantum mechanics, can actually give you a little more information of how the modification happens if your space-time was non-commutative space-time. By that I mean XY commutator is not zero. XY commutator is non-zero. Okay. So a lot of ideas are there, but then people can ask, when can you use XY commutator? We know when we can use X comma PX commutator to be IH cross. You use it only in the microscopic world, right? The Armstrong nano arena, you need the XPX commutator to be IH cross. Where do I need when I have to do X comma Y is not equal to 0 with a parameter? Planck's constant was the parameter constant one, constant, universal constant for the quantum mechanics. The non-commutative mechanics, you will have a constant which is called as non-commutative parameter. And then experiments decides when you can see it as a non-commutative theory. It might be even at a much higher energy, we need to understand how to see the non-commutative. Okay, that's one. There are also many more things like supersymmetry, even though so far experiments in Large Hadron Collider has not seen it. The tool is really very powerful. Using the tool, you can try to understand if there is some complicated potential, but you can relate that complicated potential to your potential which you know, for which you know the spectrum or the energy eigenvalues. You can try and relate by another operation called supersymmetry to get the spectrum for a difficult potential. Okay. So those are kind of mathematical tools, even though supersymmetry has not been, seen. By what supersymmetry I mean, every particle will have a superpartner. Electron will have an S electron, selectron they call it, and then they want to see whether the supersymmetry particles will all obey certain properties and so on. Okay, so those are different directions where we use the tools of quantum mechanics, but look for more general research type of things where we want to understand supersymmetric quantum mechanics. Within quantum mechanics itself, there's an ocean. Supersymmetric quantum mechanics. You can look at non-commutative quantum mechanics. We just named some of them, but there are many more topics one can. In fact, Hermitian operators, there are a huge machinery for non-Hermitian situations. So it's very interesting. If you know the basic tools, you can get back to looking at some research kind of topic, what has been done, how far it is close to experimentalists, because he was supposed to give the data from such computation. And now in PhD, most of the things are advanced research, but why we don't have much of ground level research? Ground level research also happens, not always advanced. A lot of people can find ground level some new things which have not been attempted, and you can do a ground level research. Okay, so don't worry. Not everything is advanced. The aim of running this course is at least the basic course will kind of warm you with all the tools, and then you can take off if you're doing other courses later on. Yeah, tell me. Okay. Anyone else has anything to ask? In fact, there was a article which I think appeared in the archive with one of my students where we tried to look at the non-commutative aspects, how to incorporate. Maybe if anyone is interested, you can put a name search and see it in physics archive, or we'll send a link to you. Yeah. Is that okay?
A particle in 1D box.
Yeah.
What will be the uncertainty product?
Yeah, it has to obey the Heisenberg's uncertainty principle. And maximum delta x you can have is the length of the box. Okay. Physics, I think. Bio.
Quantum physics, new.
Quantum physics. So you can check that.
This one, recent.
No, it's not recent. You have to search and putting my name. Go on. Showing all my papers. Go down. No. No. Yeah, I'll be living in non-commutative space. You can share the link with them. Mm. This paper was written with another student also, Pulkit, I think, Pulkit Gadero. So these will give you some projects which those students did and use this. Remember long back 10, 15 years ago, I think supersymmetry quantum mechanics was also done by someone. You can search. You can search in the resonance article for my name and you can check that there is article on supersymmetric quantum mechanics. Okay, so these are directions which you will be able to take off knowing the basic tools of quantum mechanics. Anything else?
Any suggestions you want to give for the exams to the students?
My suggestion is learn the concept well based on what I've taught you and try to do the exams in a calm fashion. Using those concepts, don't memorize, don't mug. That's not going to help you to do the exams. You have understood the concepts, I'm sure you'll be able to do a much, much better job with it.
How did you find quantum mechanics? I mean, you found it difficult or easy during your masters?
Who's asking?
I'm asking.
Me? It was a new concept. It took some time to get clarity. Even now, I won't say I have 100% clarity because it's very counterintuitive. So we accept certain things and we keep going. Yeah.
Can you offer an internship?
Who's asking?
It came in a
Yeah. So this summer, I am not sure whether I'm going to be around. So that is one of the reasons why I refused for an internship. And someone said, can we at least meet you in person? And I asked the NPTEL office whether that is allowed. They said if they are in the same city, they can always, you can mutually fix a time and they can meet in person. So that can be done, but I'm not sure that I'm in a position to offer you a internship this summer. Okay. So you are all college students or you're all
teaching faculty sometimes I go to
teaching? So if you are by any chance going to be in Mumbai by end of April, then we can fix a time and we can meet in person. Okay. Even in the second week of April, if you are in Mumbai, we can meet before the exam you want to meet. That also we can do. Is that all right?
this STI equation part is done still.
What is? Ma'am, STIE equation part is done. Hostel remain. What is STIE? Can you elaborate what is STIE? I don't know what is Schrodinger time independent equations. Okay. So that is what you've called it as STIE. So, yeah, so here we are not doing, are you looking at all of them which we are doing is time independent only? The time dependent is that phase factor which depends on the energy of the state. Potentials are all time independent. But you can go to time dependent or time independent also. Many times you may not be able to find an exact solution. You need to do perturbation theory. That will be the level 2 course. Right now, here we only give you a flavor of level where you have done Schrodinger mechanics, wave mechanics. Now we want to see you how to see these things as well. Okay.
So this will be the last.
So this will be the, so everything what you're doing is with the Schrodinger equation, which is time independent in the Dirac bracket notation. Yeah. Because I am having a doubt in the derivation. What doubt you have? The derivation of the Schrodinger equation? That was done as if we are looking at a free particle, and then we introduced the potential energy and we said that the Schrodinger equation is modified with that potential energy, right? And the only way, it's an empirical equation, the only way we can validate it is by experimental results. Okay. Is that all right? What doubt you have, maybe you can ask, then I will know. I thought I had derived it in the class, how to get the Schrodinger equation by looking at it as a free particle and then you introduce a potential energy. Only way you can validate is that reflection coefficient, transmission coefficient, everything is consistent with that equation. Some sense you can call it to be an empirical equation. Like we don't question F equal to MA, how you derive, right? We use that as an empirical equation. Okay. Any other question? Yeah. So if there are no further questions, most of the available software like Quantum Espresso, Schrodinger, Gaussian are based on quantum mechanics. Yes, only. If it is not 100% accurate, why we are not making attempt to correct it? What do you mean by accurate? It is anyway not a deterministic theory. It is a probabilistic theory. So that's first thing you should know, that what we study in quantum mechanics is probability. You can't say with precision that this is what will happen. You can say these are the outcomes which can happen with this percentage of probabilities. Definitely, the quantum tool is very, very important. If you understand, then there are a lot of applications in interdisciplinary areas, and it will help you to, once you learn it at this young student days, then a lot of these things you can be able to be part of it in future. Okay, then. So, if you don't have any more questions, then yeah. How it can be used in bound states where velocity is okay. So, what is bound state? Bound state condition is when happens when the energy of the particle is less than the potential energy, or kinetic energy can become negative, right? So that's the bound state condition, and you will start seeing in those harmonic oscillator, right? There are two turning points where energy is equal to potential energy. So that is the classically allowed region when energy is positive, and once it becomes negative, then it is a classically forbidden region. Because kinetic energy being negative is not classically allowed. That's why we say it's classically forbidden. Okay. So when velocity is going to be zero, then you can try to take the kinetic energy also to be close to zero, which means total energy is equal to the potential energy.
kinetic energy can
Yeah.
become.
So mathematically, if you put in, then you get a non-trivial transmission coefficient, right? If you allow this to happen, thinking that it's a wave, it can cross the barriers, then we can try to find out the reflection coefficient, transmission coefficient, and experimentally validate it. Give some tips to excel in exam, upcoming exam. See, that's all I said. I said you study all the concepts properly and answer to the question by looking at every problem. Don't memorize or do it. Okay. So learn the concepts properly and you'll be able to do the exam with those concepts. It's still an online exam, which is objective type, and it will be auto-graded. So you can still do it. It's do a much better job. Okay. Okay then. So I think we need to leave now because there's one more meeting coming up. If you have any further question, please post it on the portal and we'll take it up. Okay. Yeah.
Thanks.
So we're leaving now. Bye bye.